Hi dear students, welcome to the next topic from electrostatics, and we are going to learn about the third applications of Gauss's law. Last class we have learned about the first two applications of Gauss's law, and in these sessions we are going to learn about other two applications of Gauss's law. So the third one, electric field intensity, we are going to find using a solid non-conducting sphere. What is a solid conducting sphere? Last class we have learned about solid conducting. Solid conducting means inside it is empty. Solid non-conducting sphere, which means inside it is non-empty, it is filled, it is like an iron pipe, a fully iron pipe. So we are going to find out the electric field intensity inside, outside and the surface. So let's start. So we have a pipe is available. So we have a pipe is available and it is fully filled. So the charges are present everywhere inside and as well as on the surface of the sphere. So here also I am marking the charges, plus charges, you can mark plus or minus. So here we are going to find out electric field intensity outside, inside and surface. So first we are going to find out electric field intensity inside. So how we'll find out inside? We will consider a small Gaussian surface inside which is passing through this point. So this is at a distance of r and the original radius is r and the inner cylinder radius is r, which means I am going to find out the electric field intensity at a distance of small r meter away. So we will start. So we need to find out the electric field intensity using the Gauss's law. So we'll write Gauss's law. So closed integral E dot dA is equal to Q enclosed divided by epsilon 0. Okay. So we know it's a closed path. So we have as like I told last class, S1 surface, S2 surface and this curved surface is S3. So electric field lines are always going outside. So with respect to S1 surface and the electric field, the area vector is S1 like this and S2 area vector is like this, and this is the area vector here. So S1 surface area vector is like this, and this is the area vector at S1 surface, and S2 surface this is the area vector, and S3 surface we have this area vector. So electric field and area vector at the S1 surface is perpendicular, so that is 0. So for S1 surface it is 0, for S2 surface also it is 0, because electric field is like this and area vector is like this. E dot dA, E dA equal to E dot dA, E dA cos 90 will come. In this case, electric field and area vector will be on the same direction. So as like the continuation what we have learned in the last class, the same thing, open integral of S3 will come because S1 gone, S2 out and S3 is only in. So what is the things? E into dA of cos 0 will be equal to Q enclosed divided by epsilon 0. This is a fact. Here what we are going to do extra is that E dot dA. So of course we know E into cos 0 is 1 integral dA for this cylinder. What is the area of this cylinder? This is that area. So we need to find out the area of that cylinder. So we can find that area, and here we have another factor called Q enclosed. So I'll just hold here and I'll go to right side. Q enclosed. Here as like we have learned in the previous sessions, we have learned parameters like linear charge density lambda, charge by L. We have something called a surface charge density. So linear charge density is lambda equal to charge by length. Surface charge density is equal to charge by area. We have something called volume charge density, which is called rho. Here it is charge divided by volume. Here in case of the previous solid conducting sphere cases, inside it is empty. So it is like our normal PVC pipe, inside it is empty. If I cut that PVC pipe and open it, it is like a plate. So it is associated with sigma. But here it is associated with something called rho. Rho means volumetric distribution, because inside it is also filled. In that cases, volume will come into picture. So we'll just see what will happen. Q divided by V. V means volume of this small cube. What is the volume of that cube? Pi r square is the surface area, and the inner length and outer length both are same. So pi r square into L will be the volume of this one. And so instead of q we can replace here pi r square times of L. So we'll go coming back to the equations. E dot dA cos 0, dA surface area. What is the area of this cylinder? It is 2 pi r times of L. Okay, area of the cylinder 2 pi r, small letter r for this area. This is now our Gaussian surface. The inside one is called our Gaussian surface. Inside one is called Gaussian surface, because we are going to find out inside electric field. So right side we are substituting q enclosed. What is for q? Q, how we can write? Rho into, tell me, rho into pi r square L whole divided by, what is coming in the numerator? It is coming as epsilon 0. Pi cancel, r cancel, pi cancel, r cancel, L cancels. So what is balance will be here on the left side? E into, here we have 2 only will available. Right side we have rho is available and r is available, denominator epsilon 0. So the formula E will be equal to rho r divided by 2 times of epsilon 0. This is the electric field intensity for a solid non-conducting sphere at inside point, and from the central axis, from the center of the cylinder, which is at a distance of how much distance away? Small letter r, small r distance away, the electric field will be equal to rho r divided by 2 epsilon 0. So here we know we can write electric field is directly proportional to r. So if r is increased, so what is the electric field at the center? It is 0, because r will be equal to 0. If you are going towards outside, if I am moving from center towards outside, so here electric field more, here electric field more, here electric field more, at the surface electric field is maximum. So if you are moving from center to away from the center, electric fields will keep on increases as r will increases. So this is the electric field intensity at inside. More specifically, you can also write it as E in. Instead of writing E, you can also write it as E in, which is equal to rho r divided by epsilon 0. You don't want to write both? Just for your understandability, I told this E is representing inside electric field, which is rho r divided by 2 times of epsilon 0. Okay, so this what we have find? This we find the electric field at inside. Same way I am going to find out the electric field at outside point. So I am cleaning the board. You can pause the video and you can complete your notebook. So I am moving forward. I am going to find out the electric field intensity and outside point. So what we'll do to consider, if we have an outside point will be here, so we are going to find out electric field outside. We will consider a big Gaussian surface like this, which is at a distance of small letter r. Do not confuse, here also used a small r, here also used a small r. This are representing outside, this small r representing inside. Both are same. If you want, you can use different variables also, but for my easy understandability, normally I will use like this one. Okay, so electric field at outside, again we start with Gauss's law. E dot dA will be equal to q enclosed divided by epsilon 0. Dot should be there. As I told, we have 3 surface will be here, and this outside Gaussian surface is S3 surface, and we have S2 surface, and we have top one S1 surface. So electric fields are always towards left, always towards right. So both sides electric fields will be there. So electric field with the S3 is parallel, electric field with S1 perpendicular, electric field with the S2 is also perpendicular. So E dot dA, when perpendicular will come, cos 90 will come, that term will go outside. So what is the only term? Open integral of S3, E dA of cos of 0 will be equal to q enclosed divided by epsilon 0. Okay, we have to find out the surface area. In order to find out the surface area of this bigger part, so what is the surface area of this big cylinder? It is 2 pi r times of L, r its radius r, into q. A bigger sphere will contain some charges. What is the charges? This much charges is not present, right? Only this much charges. All these spaces are empty spaces. Our original cylinder is this one. So our original cylinder is only carrying the charges and others are not carrying the charges. So charges are only present here. Okay, so which means rho into what will say, rho is should multiplied with volume. What is that volume? Pi r square times of L. This r is important. This r is the radius of our original cylinder, which is given here. This r is our original cylinder. In case of its original cylinder is fully occupied here. When we consider inside a point, means only this much area is in picture. Other areas are outside. Outside we don't mind. What is available in the Gaussian surface only will consider. This is available in the Gaussian surface. We consider this area divided by epsilon naught. So pi cancel, r cancels, L cancels. Okay. So r, okay, here r will not cancel. Pi cancel, L cancel, pi cancel, L cancels. So what is coming? E into what all things will be here on this side, pi and L get cancels. 2 times of r will be equal to rho. And here what will come? R square by epsilon 0. So E will be equal to rho r square divided by 2 epsilon times of r. This is the electric field intensity where we have calculated. This is the electric field intensity at the outside area. So this is the electric field intensity outside of a solid non-conducting sphere at a distance of r. Here what is the relations? E is proportional to 1 by r. Electric field at the outside decreases. If you are plotting a graph, okay, if you are plotting a graph, electric field with respect to r for a solid non-conducting sphere, what will happen? Electric field intensity at inside point, E is proportional to r increasing. At outside point, it is in inverse proportion, which means it is reducing. It's going like this, it's coming like this. So E is proportional to 1 by r. This is the graphical representations of this one. This is outside. So what will happen? Electric field intensity in surface. What is electric field intensity in surface? Electric field intensity in the surface, small r equal to capital R. If I am substituting small r equal to capital R, surface means this distance equal to this. Now we are going to find out electric field at surface. So small r equal to capital R. So 1 r will get cancelled. So the electric field intensity will be, formula changes to rho r divided by 2 times of epsilon 0. This is at surface. This is at outside. This is outside electric field, as we mentioned in the heading, the same thing. This is the outside electric field. On the surface means we can substitute small r equal to capital R. We are substituting and we got electric field. So based on the 3 equations we got, electric field at the surface, E is proportional to, inside electric E is proportional to small letter r, outside E is proportional to 1 by r. So based on that we have plotted the graph. Electric field are increasing inside. Okay, electric field, if you're going from here, from the center towards right, electric fields are increasing, and electric fields increasing in sense like this, and then electric fields are reducing when we are going outside. So 3 formulas will be there. These 3 formulas should be there on your mind. So put it in a box. 3 formula plus the graphical representation for a solid non-conducting. Normally students are confused here in between the hollow conductor and solid conductor with solid non-conductor. Both are different. Solid non-conductor means inside it is filled like an iron, a fully solid iron pipe. But in case of a solid conducting or a hollow conductor is nothing but inside it is empty, like our normal PVC pipe kind of structure. Okay, hope you understood this part. We are going to see the 4th applications of Gauss's law. Okay, what's the 4th applications? Electric field due to a charge sheet. So far we have learned about something like a pipe structure. Electric field due to an infinite charge wire, application number 1. And application number 2 is electric field due to a solid conducting sphere and hollow conductor, second one. And the third one, electric field due to a solid non-conducting sphere. 3 applications already we have learned. This is a 4th one, electric field due to a charge sheet. So let's consider a sheet of charges. Okay, so we have charges plus charge sheet, and we need to find out electric field, say at a distance r from here. For example, I need to find out electric field intensity. In order to apply Gauss's law, what we need? what Gauss's law states that closed integral E dot dA will be equal to Q enclosed divided by epsilon 0. What we actually required? We required a closed path. This is just like a sheet, like an A4 sheet paper. So what we'll do here, we will consider a Gaussian surface. I consider a Gaussian surface like this. This is a closed path. So this Gaussian surface, this part I have a radius of r. Now this cylinder is a Gaussian surface. Now we'll see what is the direction of electric field intensity. Here electric field intensities are going away from the sheet because it is positive electric field like this. For this surface, this is the area vector. This is S1 surface and this is S2 surface, and area vector is like this and electric field is also like this. And we have a curved surface here also. As I told, electric field is like this. And we have an area vector is like this, S3 surfaces. So closed integral, which means S1, S2 and S3 surface all together will form this one. S1 surface with the dA, it is what angle? Theta equal to 0. Here what angle? Electric field like this, and S3 theta equal to 90. Here electric fields and area vectors are same line, theta equal to 0 degree. So which means what all the surface will finally exist for us? Theta equal to 0 exists because cos 0 will available, and this theta equal to 0 also available. Theta equal to 90 will go out. So S1 and S2 is available. So open integral of S1 E into dA plus cos 0 is already there. So if you want, you can write cos 0 plus open integral S2 E dA cos 0 plus open integral of S3. When I am putting open means all these open parts together will form a closed path. So S3 E dA of cos 90 whole together equal to Q enclosed divided by epsilon 0. These terms will go out because cos 90 is 0. Here we have E dot dA. This is a one surface area and this is also one surface area. Okay. So this area open integral S1 EA plus. Okay, integrated dA integrated to A plus E into the second one EA plus, the third one is 0. So which means Q enclosed divided by epsilon naught. Okay, charge means the total charge on the sphere. So this is 2 times of EA will be equal to Q enclosed divided by epsilon naught. So electric field E equal to Q enclosed divided by 2 A epsilon naught. What is charge by surface area? Charge by surface area, I told one term is called sigma. Charge by area is called sigma. Sigma surface charge density. So we can written this formula as sigma divided by 2 epsilon 0. This formula is very important. Lot of questions are already came for entrance examination. Electric field intensity due to one charged sheet equal to sigma divided by 2 epsilon 0. Nothing else. We applied Gauss's law, what we have done for section number 1, 2 and 3, and in the fourth application also the same story is repeated, but here we have two surfaces are parallel, this available and this available, and this area A is nothing but what is called pi r square. If you want, you can substitute, or instead of that I just keep it as A. So Q by A is called sigma divided by 2 times of epsilon 0. I'll tell you how the questions are coming from this area. We'll take one example and we'll see how the questions are forming from this area. Okay, so you can pause the video as usual and you can complete your notebook with this till sigma divided by 2 times of epsilon 0 formula. Okay, so let me take an example in the sense how a questions are coming normally from this area. Suppose I have a sheet like this. Okay, I have another sheet like this. Okay, this is positive sheets and this is negative sheets. Both are equal area. Now I am asking you, what is the electric field at position number 1, at position number 2, at position number 3. 3 point you want to find out electric field intensity. Same sheet, same dimension, same charge density. So with respect to the first plate. Okay, with respect to the first plate, electric field lines are going outside. This is plate number 1, this is plate number 2. So electric field E1. So for second, from the point to the second plate is a negative plate. Negative plates will attract the electric field lines. So E2 will go like this. Okay, here positive plates will push the electric field. Negative plates, what will happen? Attract the electric field. So at this point, E1 and E2 in the same direction. In case of third, first plate will push, so going away. So electric fields are going away, E1. Second plate will attract the electric field, so which is like this, E2. Okay, so what is the value of E1 and E2? E1 is equal to E2 is equal to sigma divided by 2 epsilon 0. What this means? It is independent of the distance. If I'm measuring here, if I'm measuring here, if I'm measuring here, everywhere it is same. So sigma divided by 2 epsilon 0. Here E1 and E2 are same. Here E1 and E2 are same, and electric field is a vector quantity, and both are same and both are directing in the opposite direction. So what is the total electric field will be here is equal to 0. What's the total electric field will be here? Two vectors, both are in the same direction. I can add it up. Sigma divided by 2 epsilon 0 plus sigma divided by 2 pi epsilon 0. 2 sigma by 2 epsilon 0. What will come? Sigma divided by epsilon 0 is electric field intensity at the middle position. This is for different sheet. Okay, so electric field is exist between this area. This is what we are going to see after a few sessions of the class, something called capacitor. Capacitor means positive plates will be there, negative plates will be there. Between the plates, electric field is exist. Between the plate, electric field is exist. Electric field exist means energy exist. That's all. We will see in capacitance sessions. But remember that I have told you something before, sigma by epsilon 0. What is here? Electric field right side and electric field left side. Both are vector quantities, both will cancel. So what is electric field here? Electric field will be here is equal to 0. Here it is equal to 0. Here is equal to sigma by epsilon naught. If it is an opposite plate, positive and negative plates, electric field only exists at the center, which is sigma by epsilon 0. I will give you a challenging questions to you. If both are positive plates like this, if both are positive plates like this, what is electric field at 1? What is electric field at 2? What is electric field at 3? Think about this one. If you have any doubts on something, just come back to me. Instead of positive plates on negative plates, I placed a positive. What will happen? You know the answer, right? Positive plates mean electric fields are going away. So if you're considering one alone, I will tell you. 2 and 3 you can answer, right? With respect to 1, from the plate number 1, plate number 2, electric fields are going here. And with respect to 2 also, electric fields are going here. So what will happen? 2 electric fields will be here. E1 will be here, E2 will be here. 2 are vectors. 2 vector quantities are directing in the same directions. What you can do? You can add this one. So what will happen? Sigma divided by 2 epsilon 0 for one plate. Another plate sigma divided by 2 epsilon 0. If you're adding these two, what you will get? Sigma divided by epsilon 0 at the left side. At this point, it is sigma by epsilon 0. If it is a different plates, what is on the left side? It is 0. If it is the same plate, what's on the left side? Sigma by epsilon 0. Answer will be changes. Similarly, you can find what is at 2 and what is at 3. Okay. 3 also, both you can imagine, right? The electric field due to 1 is going like this, and because of 2 it's also going like this. So both are going the same direction. You have to add, you will get the same thing as like here, sigma by epsilon 0. But at the center, what will happen? Electric field due to 1 is like this and 2 is like this. Both will get cancelled. So electric field is not exist if both are same plates at the middle, and electric field exists on the left side and electric field exists on the right side if both are in the same plate. If both are with the different plates, electric fields are exist only at the center. What is electric fields coming here? As I told, the same thing, right? Sigma by epsilon 0. Here we have E1 and here we have E2. What will happen? Here we have E1, here we have E2. So E will be equal to 0. So they can create any combinations like this, plus with minus, plus with the plus. Same thing you can do with minus with minus. So questions may come in any fashions anyway. Hope you understood this one. So try to enjoy with Gauss's law, such a beautiful law, and make our life easiest to find out electric field intensity for different shapes. Okay, thanks and have a nice rest of the day. Bye.